This is the second video lecture for Chapter 4 in EE211 Circuit Analysis 1. In this video we will cover Thevenin equivalent circuits, Norton equivalent circuits, maximum power transfer examples and calculations, and do some modeling with multisim, and I think we'll also cover the Wheatstone bridge. So Thevenin's theorem is a way to make an equivalent simple circuit. So in many circuits, the one element will be variable, like we call this the load element. If you think of a power distribution within a neighborhood, the houses change how much power is being consumed and how much resistance is being presented to the source, which is the power company. So this variable element is called the load. You can also think of a lot of other things, circuits that turn off and turn on, or circuits that start processing something. And for example, making this video, my computer is working harder and it's using up more, dissipating more power. So this is a variable load. So we want to be able to model the source as one source that can and understand how it will behave with a bunch of different loads, not have to reanalyze the circuit over and over again. So that's what we use Thevenin's for. Actually, you can use Thevenin two ways. Your book uses it to simplify and model the source, but you could equivalently make a Thevenin equivalent of the load. So Thevenin's theorem states that any linear circuit with two terminals on it can be replaced by one equivalent voltage source and one equivalent resistance. So this linear two-terminal circuit can be very complex inside. There can be a lot of circuitry inside, but you can actually, by measuring it, you can simplify it or model it as one equivalent source, which we call V Thevenin, and one equivalent resistance, which we call R Thevenin. So this value of V Thevenin is the same as the open circuit voltage here, and I think the example next and my additional instructions will make that clear. And the resistance, the R Thevenin, is the resistance that you would measure between these two terminals if the source, everything in the source is turned off. So, and then I do note here that although your book wants to model the source with a Thevenin equivalent, I could equivalently model the load as a Thevenin equivalent. So there's two cases to consider, just like our previous analyses. We had to consider whether we had all independent sources or whether there were dependent sources involved. So case 1 says there's no dependent sources, which is always the easier case. And then you may find the resistance by turning off all of the sources and measuring or calculating the resistance that you find at this terminal between the terminals A and B. So turn everything off, measure the resistance, turn everything off, calculate what the resistance is, and then you get R Thevenin. The V Thevenin is found by, of course, you have to take the load away, and just measure the voltage between these two terminals, or calculate, as the case may be in our examples. So case 2, that there are dependent sources. This is more complex. So first thing is you turn all the independent sources off, but you always have to leave the dependent sources on, and you put some voltage here. It's nice to use 1 volt because it's a convenient number, and then you analyze the circuit and you find out what R Thevenin is because of this voltage that you assumed here, like maybe it's 1 volt, and then you'll figure out what the current is. Similarly, you can short circuit the output and determine what the voltage is here. And then you have to make calculations to determine this Thevenin equivalent going on here. So procedure in general, remove the load, take it off, open circuit it. then determine the voltage at the load terminals by standard techniques. In the lab you would measure it, and in homework you're going to calculate it. But you keep all of the internal current and voltage sources turned on. That will give you Thevenin. Then you turn off all the sources inside, which means what? It means if it's a voltage source, you short it out. If it's a current source, you open it. Make it an open circuit. So after you turn off everything in the source, you measure or calculate the resistance, the equivalent resistance. That's R Thevenin. And then alternatively, you could keep the sources turned on and short circuit the output with the load missing and determine the current there. And that will give us Norton's equivalent. So when I was in engineering school, this was a very confusing thing here, but keeping in mind exactly the procedure you have to follow, it'll start to become more clear. So let's do it first by example. This is an example not worked in your textbook. It's actually practice problem 4.8, which they give you the answer for, but they don't work the problem for you. So this is example 4.8. So here's the whole problem, and you want to find the Thevenin equivalent between terminals at A and B, and this is the load on this side. So step number one is remove the load, open circuit it, take it off. So here is the circuit now with the load removed. You have to do all the analyses without the load. So we did that. So step number two, let's find V Thevenin. So if I want to find V Thevenin, I leave all the sources turned on and I just determine what the voltage is between A, B. So in this case it's the voltage between A and B. And you do that in the lab, you go in and measure it, but in a homework problem you have to just use your standard KCL and KVL and calculate what's going on. So I'm going to use KCL because I see a current source in there, and when I see a current source I generally like KCL. I'll call this node right here voltage at X, so I can do KCL. I'm going to assume a current this way, this current goes this way, so that's two ends. I'm going to call this the out current there. So I1, I2, and of course I2 is the same current that's right there. So let's do KCL at the node at Vx. So I know there's 12 volts right here. Here I'm going to call my reference 0 place. I'm going to put my, polarity, that's a minus sign, polarity markers on everything. Current going in is at a higher potential here than when the current comes out. Okay, so we'll do KCL at that node. So 12 volts minus voltage at X divided by 6 ohms. That's an application of Ohm's law right here. The voltage drop across that resistor divided by the resistance gives me current, right? Actually, what am I doing? I'm saying I1 plus 2 amps equals I2. And now I'm applying Ohm's law. So this is I1, and then plus 2 amps going into the node equals the current leaving the node, I2, which is Vx. So voltage up from here at that node I call Vx, and Vx, that current is Vx divided by 6 plus 4 ohms. So that's this current in this branch right here. And these are just measurement places. Nothing is going on here. These are just references to the node. So I have one equation here, one known Vx. I can do the algebra, and when I do the algebra I'll get that Vx equals 15 volts. So now I can go back and find this current right here, and once I find this current right here, then I can determine the voltage across the resistor. So Vx divided by 6 plus 4 ohms equals I2, that will turn out to be 1.5 amps, right? 15 divided by 10 is 1.5 amps. So now I can find VAB, which is my Thevenin voltage. So V Thevenin equals I2 times 4 ohms, which equals 6 volts. And I think that's the answer. The textbook, yes. Textbook said V Thevenin was 6 volts. So we found the first thing. We found V Thevenin. So we know if we were going to make a Thevenin equivalent of this circuit right now, let me go forward one slide. Okay. If we were going to, if we were going to make a Thevenin equivalent of this circuit right now, we have the first thing determined, which is V Thevenin. So we still need R Thevenin. And there's the terminals A and B, where we would attach the load later on. So this is the equivalent circuit that we want to get from this. And this equivalent circuit is going to supply whatever the load needs, and you can model it this way. Okay, so now we need R Thevenin. For R Thevenin, that's step 3. We're going to find R Thevenin. For that, you have to get rid of all of the sources in the network. So for a voltage source, that means short it out. For a current source, that means open it up. And then determine the resistance as seen by these terminals. So if I put my voltmeter between terminals A and B, what resistance would I see? So I see that that's really a series circuit that looks like this. 6 ohms, 6 ohms, 4 ohms, and here's my A and B points. So that's 12 ohms in parallel with 4 ohms, which is 12 times 4 over 12 plus 4, which equals 3 ohms. So I now have R Thevenin is 3 ohms. I have now completely determined the Thevenin equivalent of this circuit, 3 ohms and 6 volts. And so I can put my load resistor on here and determine what the current is by doing an analysis with this whole big circuit here, or I can put my 1 ohm resistor back on, 1 ohm load resistor here, and analyze this circuit and determine what the current is in there. So step 4 was determine the load current, I load. So I did that by first finding the Thevenin equivalent, and then I analyzed the circuit, which is your standard series circuit, and I can find out that I load is 6 volts divided by 3 plus 1 ohms. 1 ohms. So 6 divided by 4 equals 1.5 amps. So that's the load current. For Norton's equivalent, my hand makes that do that. For Norton's equivalent, you can take off the load. So here my 1 ohm resistor has been taken off, and I short circuit the output. So I'm going to find I short circuit right now. So SC for short circuit. If I do that, I leave all the sources turned on, and I find the short circuit current. And so I'm calling this a VX again. This looks like a, this is another case of using KCL to find this current. So when I short this resistor out by putting this short right here, this resistor is gone. It's been shorted out. So it's no longer in the circuit anymore, and I have this loop going on. So if I go ahead and write my node equations for here, I have, let's call this I1 again. and we'll call this I2. So I1 plus 2 equals I2. I1 is 12 volts minus Vx over 6 ohms plus 2 equals I2 is Vx over 6 ohms. And then I solve for Vx, and I find out that Vx is 12 volts. I come back and find out I short circuit, and that is going to be Vx divided by 6 ohms, which is 12 divided by 6, which is 2 amps. So I claim, oh, by the way, and then you find R Thevenin the same way as before. So I'll just use R Thevenin from the previous side, which was 3 ohms. So I'm going to go ahead and say I'm going to go ahead and say we have 2 amps, we have 3 ohms. This is I Thevenin, this is R Thevenin, and we have terminals A and B, and then we are going to, when we're ready, attach our 1 ohm load resistance right there. Whoops, 1 ohm, which is our load. So this looks like a source transformation thing. So what if we did a source transformation? So I can convert that to a voltage source, which is this resistor times that current, which comes out to be 6 volts. And then resistor now goes here. And lo and behold, it looks back to the same. This was the Thevenin circuit. And the equivalent is the Norton circuit. You get the Norton circuit by finding I short circuit. You get the Thevenin equivalent by finding V open circuit. So when we were finding Thevenin, we open circuited it and found a voltage. Open circuit, found the voltage, found the resistance like normal ways, with everything turned off. And for the Norton equivalent, we 1. Remove load, 2. Turn off everything, find R Thevenin, 3. Short circuit, the output, and then find I short circuit, which is I Thevenin. So, but by source transformations, these two things are exactly the same. So I was going to show you in multisim this example as well. So here is the original circuit with the load on. So let me run the simulation right now. So simulation is running right now, and my probe is right here, and it is indeed supplying 1.5 amps, which is what we calculated that it would do for the load. It's actually 1.5 amps and 1.5 volts right here at the load terminals. Okay, so that's all well and good. Remember that the load is getting 1.5 amps and it has 1.5 volts across it, and then over here is the complex source circuit. So I'm going to stop that for a moment. Now I came over here and I drew the Thevenin equivalent, which I forgot to change the values, so let me change the values real quick. It was 6 volts, which was the V Thevenin, and R Thevenin was 3 ohms. So now I have the Thevenin equivalent here, and I put my 1 ohm resistor on, the load resistor on. I'm going to run the simulation again, and sure enough, across the load it's 1.5 volts and 1.5 amps. Okay, well that's just what we did. So now let's go back to the original circuit and let's change the load to some other value. I'm going to make it be, oh, I don't know, something that makes the numbers weird. 7 ohms. So this load is now 7 ohms. I will run the simulation. So at 7 ohms, we have 600 milliamps in the load and 4.2 volts across the load. So my claim is I've made the Thevenin equivalent, and it should be exactly equivalent to the original more complex circuit in what it can supply. So I changed my load to 7 ohms, rerun the simulation, and yes indeed there is 4.2 volts across it and 600 milliamps across the load. So this model of the equivalent source is valid as the load changes. So whatever the load is, modeling the source this way, and see I didn't have to change anything in the source, modeling the source this way will let me completely understand what's going to happen at the load. Alright. So this is a very powerful tool actually in circuit analysis, and because it lets you simplify the circuit. And a large circuit may be replaced by a single source and single resistor. So and then the equivalent circuit behaves externally exactly like the original circuit does, which I just showed you. Now, when you put dependent sources in the mix, sometimes you can come up with a negative value for our Thevenin. That just means that the circuit is supplying power. Nothing wrong with that, nothing wrong with getting a negative answer. It is a almost a theoretical condition, but it's like all of the loads are supplying some power to it. Okay, Thevenin versus Norton, these two are exactly the same. We showed that you could just look at source transformations and then you see that they are the same. So the Norton current is also called the short circuit current, but they were all related through an Ohm's law. Now let's look at maximum power transfer. So, the circuit is designed, the source is designed to deliver power to a load, but there are cases when you want to maximize that power that's transferred to the load. This especially occurs in RF circuits, and we want to have maximum power transferred to in an RF circuit or in an amplifier condition. Speakers are another example of having to have maximum power transfer. So, but the source, the thing that's powering, is not ideal, and as a matter of fact, the source can be modeled as having a equivalent source voltage. It's a Thevenin and an equivalent internal resistor. So the fact that real sources are not ideal and they have some kind of internal resistance affects how they perform, how they deviate in their performance from the ideal case. So here's an example. This should look familiar from lab actually, of doing maximum power transfer. So if I have a source right here and I've already modeled it into a Thevenin equivalent, so it's equivalent to one source and one resistor, there is a point which you saw in lab when this resistor is optimized so that you get maximum power across this resistor. And the source can supply whatever current is dictated by this circuit. So there is a point where the power will be optimized here. Just as a simple circuit analysis right here, you can find out the power in the load. This is in the load. So power in the load is I squared R load. If I do a little loop equation here, that's voltage, the current is voltage divided by these two resistances squared times R load. So that's power in the load. And then you saw in lab that as you varied the load resistance, there was a place where the power transfer was at a maximum. This is actually, the value of that load resistance is when this load resistor exactly equals this load resistor. When you have that condition, you get maximum power transferred into that load resistor. So, how do we prove that? So if you recall some from calculus, that when you take the derivative of a curvy line like this, when you take the derivative, you get the slope at that particular point. So if I take the derivative right there, I'll end up knowing what the slope of the line is. If I take the derivative of this curve right here, the derivative will be 0. The slope of that line is 0 at this point. So we're going to use that fact in order to prove that maximum power transfers occur, power transfer occurs when our Thevenin and our load are the same value. So I said you have to take the derivative of the power curve with respect to the load resistor and set it equal to 0, because when the derivative equals 0, you've found that point on the curve. So take the derivative of power with respect to the load resistor. There's just the calculus of taking the derivative, set it equal to 0, and when you do that, you indeed find that our load must equal the Thevenin resistance, or the internal resistance of a power supply, and then you have maximum power transfer. If I substitute that back into the power equation, I get a simple equation for what the maximum power transfer is. So for modeling, Thevenin and Norton are very useful of understanding how realistic sources behave, because, as I said, realistic sources do have internal resistance, whereas the ideal ones are assumed to have, for a voltage source, they're assumed to have no internal resistance, and current sources have infinite internal resistance. So, but that's not true in the real world, and when we make a Thevenin or Norton equivalent model for the source, then we can see how really our load would behave with a non-ideal source. So here's a specific example when we were doing power transfer, for example. So I have my source modeled as a voltage with some internal resistance. So this is my power supply now. And if I were to short circuit my power supply, I would not be able to put out this voltage source. So let's say I set that at 12 volts, but I short circuited my power supply, I would not get 12 volts out. So it turns out that then if I start giving just a little bit of resistance, which is a whole lot of current, I still cannot supply the 12 volts that I maybe want for my circuit. But as my load resistor gets a little bit bigger, I am no longer affecting so much how much current is in that loop, and I can start to actually approach the fact that that this voltage here will be close to this voltage out here. So that's what we're showing. We can demonstrate that in the lab. You can short out a power supply, and you'll see you will not be able to get the voltage out. Similarly, a similar thing happens with a current source. So here's a current source powering some kind of a load. If there is no load here, or if you short out this load, I should say, if I short out this load, you get the full source current going through the loop, right? But as I increase this resistance, I am deviating and no longer being able to get this full current into the load. So that's the deviation between, the difference between an ideal source and a non-ideal source. So we're going to do the next example here is example 4.14 in your book. Your book did a Thevenin and Norton equivalent circuit using PSpice. We're using all multi-sim here, although the book example chose to use PSpice. So I'm going to do this example in multi-sim for you because I want to find a Thevenin and Norton equivalent, but we have a dependent voltage source in here, which complicates how we find Thevenin and Norton equivalent circuits. I have the circuit partially drawn out here in multisim, but I wanted to point out a few things. First of all, this has a dependent voltage source. It was a voltage controlled voltage source. So the voltage at this source depends on the voltage across here. It can also be a current controlled voltage source. But let me just show you where that component is and how to use it. So place component. It's in the sources, and it's in the controlled voltage sources. So if we had a controlled current source, it would be here. But it's in the controlled voltage sources, and then you come over here and you have a few more choices. These are used for simulations actually, but there's a voltage controlled voltage source right here, and this is the one that you want. So if I would then place it on my schematic, but it looks like this. So the way you use it is, this is the dependent source, but you have to tie this to the voltage that you are depending on, and mind your polarities here as well. So I'm dependent on the voltage with this being plus and this being minus that's across R3. So I need to connect this that way because this is its reference point. Actually, to do that, I can just, there's the minus side, correct? This is still the minus side. And then the plus side has to be the plus side of R3 here. So I don't know what's the prettiest way to connect that. So I think I'll do that. So these nodes are not connected. But so now the circuit looks a little bit messy, but understand that this is how I am making this a dependent source. Okay, so recall that this is case 2. If there are dependent sources, we still have to turn off the independent sources. Then we apply a voltage to the output terminals and determine the current. So apply a voltage, determine a current, and then we get our Thevenin. So let's do that in our circuit. So let's see, I want to find Thevenin, so that means I have to get rid of independent sources. In this case, it's a current source. So I'm going to delete it. So it's gone from the circuit right now. And then I have to apply a voltage here, determine the current, and then I will be able to find our Thevenin. So let's place a voltage source there. Place component. This time it's just a plain ordinary DC voltage. We'll do it for a single point right now. Oh, DC power, yeah. We'll put a DC in here. And I'm just going to, oops, sorry. Go back to where I was here. I'm going to put some nice value in here, 1 volt. Okay, and connect up the rest of the circuit. So remember, I have my user options somewhere set so that I can see these node numbers. Let's just put let's do it the simple way right now, and then I'm going to show you the more complex way that the example in the textbook was showing you. I'm going to put on a measurement probe because that's really easy. There's my measurement probe. Let me make it so you can see it. Oh, that's probably good enough. Okay, I think you'll be able to see the output now. Of what's happening there. Well, gee, you know what the voltage is going to be, so really it's a matter of what the current is going to be there, correct? So let's just run it for a minute. It does not look like I'm allowed to run at the moment. Why am I not allowed to run a simulation? Let me figure that out, because run is not available. Maybe I left a simulation running over here on one of the other circuits. Yes, I did. Turn that off. Okay. Now I should be able to run a new simulation. Yep, I can. Okay, pause or stop it here for a minute. So notice that I have a negative direction there, which is a negative resistance. But this is so if I put 2 volts in there and run it again, then at 2 volts we have that value. So I have 2 volts is minus 333 milliamps. 1 volt is minus 167 milliamps. I can, let's go back to our example slide where we're doing this problem. This one right here. Okay, so I injected 2 volts at the end of it. So I have 2 volts. I get minus 333 milliamps, and at 1 volt I get minus 167 milliamps. So our Thevenin is going to be the change in voltage over the change in current. So 1 volt divided by, okay, so that's the same, isn't it? Volts divided by this difference right here, 333. Let me calculate it. I should have calculated it first. Yes, that's what I thought. It's a divide by 2 thing here. So it would be minus 1. If I do that, I get R Thevenin equals 2 volts divided by 333 milliamps, which is going to give you the exact same value as R Thevenin, which is 1 volt divided by 167 milliamps. But I want to show you some additional features since they wanted to show you slope. Slope is always the same, so yes, that makes sense. Why you didn't have to have, you could just use 1 point on here. But let me show you how to change the simulation to do something similar to what the book has. So back to the simulation here. Actually, that wasn't the right source for what we're doing. So I swapped out that parameter controlled source and put an ordinary voltage source here. It happens to be 12 volts, but what I want to do is a DC sweep so I can make a slope like shown on page 153. So let's go ahead. I'll show you a different simulation. The analysis we're going to do is called, so there's a bunch of different choices here. We're going to do a DC sweep. And it says select your source. So I'm going to make my source be V2. V2 is right here. But it doesn't matter that it says 12 volts right now. I'm going to start it at 0 volts. I'm going to stop it at 5 volts. And I'm going to increment it in half volt steps. Click over here on the output tab. And this means I in resistor 1, I in resistor 3. But I already, if I wanted resistor 3, I could put it there, but I don't. I look back at my circuit and I want I in resistor 2. So there's I in resistor 2. That's the output that I want. There's some options here. Just use the defaults. You can see underneath multisim is PSpice. Actually, it's Spice underneath. And then there's a summary of what we just set up. So there's all the analysis parameters that we set up. Let's simulate, and there's the results. So there's the output voltage, or our injected voltage going between 0 and 5 volts, and there's the output current here. And when we get the slope of that line will be 6. It's actually -6, and your textbook has it as a +6. Okay, so next example that I have was demonstrating maximum power transfer. That's this circuit right here. I'm going to demonstrate it just by putting a simulation that will exactly repeat what you did in the lab. So I can build this circuit really quick right in front of you. The simulation's not running. Great. Actually, let's use this circuit right here. We want to make this a resistor that varies. In the place components, I didn't find the variable resistor, so I think I'm going to leave that 7 ohm in here, and I'm going to change the type of simulation that I'm going to do. My simulation is going to be a parameter sweep. So parameter sweep should let me change some of the parameters of this circuit and sweep it. So I'm going to sweep a device. I'm going to pick a resistor. I'm going to pick R2 to vary it. Right now it's a resistor with its presence value of 7 ohms. So I'm going to do a linear sweep. I'm going to start it at 0 ohms and go to 10 ohms. I expect it to be the maximum power transfer to occur at 3 ohms. So okay, we'll start at 0 and go to 10 ohms. If I pick 11 points, so that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's 11 points. So if I pick 11 points, then that's an increment of 1 ohm. I could do AC analysis, DC operating, transient. I want a DC operating point. I want to know where the circuit is operating for each value that I changed the resistance or the parameter. And I would like to display results on a graph. I can display on a table or I can display on a graph. So I'm going to display my results on a graph. The output that I want to see, I've already played with this a moment ago, but the output that I want to see is power in R2. So I put power on in R2 for the analysis. So let's click on simulate, see what we get. So there it is, and indeed this is the resistance going between 0 and 10 ohms, and then I can see what the power is, and there is indeed a point of maximum power transfer which we can calculate. I could have also shown that in table form and then exported that to Excel or something if I wanted. So you can export this data value. So it's kind of nice to see the plot though. I like multisim. Okay. I guess I'll put that plot in here. So go back to multisim for a moment. I don't have it going anymore. I have to run it again. Okay, simulate it again. Simulate analyses, doing parameter sweep on a graph. There it is. And I will stick it in for my results on this slide. Yay! Okay, so there it is in multisim. Actually, if I want to, let me show you a few other things. Oh, I'm done there. I can also copy and paste these circuits, which is kind of convenient for when you turn in your homework. So there's my circuit in multisim. And the analysis that I used for, whoops, we're going to use the parameter sweep for the simulation. Alright, I think I have one more thing to cover in this chapter, which is the Wheatstone bridge. So, now the last part of this presentation we're going to cover the Wheatstone bridge. Wheatstone bridge is a circuit that confuses a lot of students. It did when I went to school too. So I'm going to try to simplify it, looking at it, and hopefully it'll be helpful. So Wheatstone bridges are a very accurate way of measuring resistance. We use ohm meters, and that's very common and convenient. But if you wanted to be very, very accurate, you would use a Wheatstone bridge circuit. But let's go through and analyze it, show how it works, and maybe take some of the difficulty away. So this is one rendition of a Wheatstone bridge right here. So there's 4 resistors. I'm going to redraw it in kind of the traditional diamond shape that you often see it. And then between these 2 nodes is a thing called a galvanometer. So a galvanometer works on Faraday's principle, I believe it is actually. So when current is going through this coil right here, it creates a magnetic field and it deflects the needle. So it essentially has very little resistance, only the resistance of a coil of wire, and it can measure the current going through here. And there's a picture of one. And I can demo it for you in the lab too, because we have a bunch of them sitting around. So when you get this Wheatstone bridge balanced, then you'll have no current through the galvanometer. And that's how you can use this configuration to determine an unknown resistance. So let me just look at it from kind of a practical and simple way to analyze the circuit. And I'm sorry I don't have the circuit pasted in here in advance, but I think we can work with it. So I'm going to draw a circuit. I'll pick some voltage here and maybe 40 ohms, and then an unknown guy that we want to know, and just to be, I don't know, I'm making up numbers as I go, so just to do the example, and 200 ohms. So there's my complete circuit here, and of course we can put our little galvanometer here. But I want to point out something here. So this is really an application of voltage dividers. I have 10 volts right here, and pretending this galvanometer isn't here at all, what do we really have in this circuit? Let's get rid of my, ooh, why is it beeping? Okay, so we get rid of this galvanometer right here. I have 10 volts here, I have 0 volts here, and this voltage at here, voltage A, I'm just going to make it be a node, and this one right here is going to be voltage B. What is really the voltage A there? It's really a voltage divider. It's 10 volts times R over R plus 40, and that's what the voltage is at voltage A. What's the voltage at voltage B, at node B? Similarly, it's 10, and then it will be 200 over 90 plus 200, because it's a voltage divider. This right here is just a voltage divider. So if I equate these two, it will become a balanced resistor. If voltage A equals voltage B, no current is going to flow through this center part because there's no voltage drop. And this is the principle. So we want to make the Wheatstone bridge become balanced, and then no current will flow through here, through this galvanometer, because there's no voltage drop. You can't have current if there's no voltage drop. And at that point, when it's balanced, you can determine that unknown resistance. So then I just say voltage A is going to equal voltage B when it's balanced. So this A equals B immediately you see that this voltage over here doesn't make any difference at all, and you get R over R plus 40 equals 200 over 290, which is something you can solve for, but you can very, very precisely find out what the tune this resistor, vary this resistor, and find out what it is. Likewise, you can determine the value of an unknown resistor, which would be an unbalanced Wheatstone bridge case. So here's balanced. When it's balanced, this is how it behaves. Let's look at the unbalanced case now, because this is where it gets more interesting. So when you put an unknown resistor in the circuit, you really have an unbalanced circuit. And so the way you would use this Wheatstone bridge to determine the value of the unknown resistor, it's kind of summarized right here. You put the unknown resistor, but you put it in series with a variable resistor. Now you have some boundaries, like you can't put your variable resistor in there that's way off target. But this is essentially how you do it. Going back to the circuit I just had drawn a moment ago, I'm going to change this resistor to some variable resistor, but if it's an unknown resistor, I probably have a variable resistor in there and my unknown resistor, so there's a total resistance there, and you will adjust this total resistance there until you get your Wheatstone bridge to be balanced. So it does take some knowledge of what range of values based on these other known guys that you can work with, but then you can very precisely measure the unknown resistance that's in the circuit. So this slide sort of summarizes it. When balanced, the unknown resistor's value is a voltage divider equation. But we are going to look at the case when there's an unbalanced resistor, which is similar to the problems at the very end of this chapter. Actually, I think I'm going to actually do practice problem 418, which has an answer, but it's not worked for you. So here it is. This is, and that's the answer they give, but they don't work the problem out for you. So there's a galvanometer in here. It has an internal resistance of 14 ohms, and in an unbalanced configuration, and it says determine the determine the current that's in the center arm here. So they give you this problem is for you to practice your use of Thevenin equivalence, because that's the practical way to solve this problem. I could write loop equations, and I could also solve the problem and find out what the current is. So technically I could do a loop equation here, do a loop equation here, do a loop right here, 3 loops, and find out what the current is in this branch. So that would be one way to solve the problem. The other way to solve the problem is using Thevenin, and this is a chapter emphasizing using Thevenin, so let's go ahead and do that. So the first thing in Thevenin, this is the load right now between these terminals. So we want to know what is the current in this load. So that's, for all intensive purposes, that's our load. So step 1 in Thevenin, what do? We take off the load. And I'm like this believer in redrawing circuits, but pretend the load is not there. But before I redraw the circuit, step 2, if we want to find our Thevenin, what do? If we want to find our Thevenin, you have to turn off the sources. So this is the only source down here, this 16 volts. So I'm going to turn off the source, and then at that point I say, what is the resistance? So here's where you have to be good at visualizing things, or you redraw the circuit. In my case, I like to redraw the circuit. So I will call, I'm going to call this point A and this point B. And so connected to A, what do I have? Between, this is gone, remember this is gone right now in the middle. Actually, I can make that be gone very well. I'll just remember this is gone right now. It's not in the circuit. So between A and B, what do I have connected? This is gone also, because I'm finding Thevenin. I have a 60 ohm resistor and a 20 ohm resistor. So from A, I have a 60 ohm resistor, and I have a 20 ohm resistor, and it connects back up to point B. That's one path. I have another path between A and B, and it happens to be a 40 ohm resistor and a 30 ohm resistor. So that's the resistance between terminals A and B. That's the resistance that I see looking back at the circuit, as we say. So this is something that's very solvable. That's a 70 ohm resistor in parallel with a 80 ohm resistor, and when I do that math, I will get 37.333 forevermore ohms. Okay, good. So I have R Thevenin. How do you find V Thevenin? So V Thevenin means put the source back in. I think this is going to beep when I erase, but yeah, sorry. Sorry about that, those beepings. I'm on a different computer today, and it seems to work different. My pen seems to work different with this different version of PowerPoint, a lower version of PowerPoint. So it says put the source back in and measure the voltage between terminals A and B, with the load not in. So it's a little bit tougher to visualize, but I don't have the load back in right now. I do have the 16 volts, and if I kind of redraw that circuit, just because I don't know, I think I get used to looking at things certain ways, and so I redraw them into that way so I can visualize things better. Do what works for you, of course. 20 and then a 30, and then it goes back to the 16 volts over here. So I have the load not connected right now, so what is this? It's a simple voltage divider, and so I can find, this is A, I can find voltage at A, and I can find voltage at B. So if I do that, VA is 40 over 60 plus 40 times 16 volts. Correct? Yes. Which I calculate that out to be 6.4 volts. And VB is 30 over 20 plus 30 times 16 volts. And I get VB is yes, 9.6 volts. Okay, so now it says what is the current in there, but I have, at this point I have V Thevenin, because V Thevenin is this voltage. It's the voltage drop at the open terminals right here with the source put back in. So V Thevenin is VA minus VB. In the way I've drawn it, that actually makes me have a negative voltage, but that's okay. That doesn't affect us. 3.2, it's 9.6 minus, or 6.4 minus 9.6, which is negative 3.2 volts. So really we know that voltage B is higher than voltage A because I got a negative value, and my assumption is that A is positive and B is the lower potential. So I have V Thevenin now. I can go and draw the Thevenin equivalent circuit. Did I give myself another slide? I did not. Okay, so I'm going to draw my Thevenin equivalent circuit right there. There's V Thevenin, negative 3.2 volts. I have R Thevenin right there, 37.3 ohms. And I have my galvanometer load put back in, which was 14 ohms. At that point, I have a circuit that you are very used to seeing, and then you can calculate what the I is. So I calculated, I actually got the answer was 62 milliamps, but I could have a calculation error in there. But the point is, I made a Thevenin equivalent of this circuit by removing the load, finding R Thevenin and V Thevenin, and then I put the load back in, and I was able to determine the current that's going through the galvanometer arm of my Wheatstone bridge. So I hope I simplified Wheatstone bridges a little bit for you. They're something that give engineering students a hard time. So that's all. That's the end of chapter 4.